Greetings everybody, it is that time of the year once again where we go back and take a look at some past VCAA exams. So what are we doing today? We're taking a look at the Methods 2020 Exam 2, only the multiple choice because I don't want to do the whole thing, can't be bothered. So yeah, this was the exam I did back when I was in year 12, and turns out I haven't done a video on this yet, so might as well do it and revisit some nice old memories and whatnot. But yeah, let's just jump straight into it. This is a tech active exam, so we got our CAS loaded up over here. So yeah, question 1. Let f and g be functions with all these conditions. We want to find the value of g of f of -1. So what is f of -1? It's 4. What happens if you plug 4 into g? It's going to be exactly 6. So the answer is D. Next up, we've got a polynomial when p is divided by x plus 2. Looks like some remainder theorem over here. So we have the remainder is 5. So if we plug -2 into this polynomial, we should get 5. So what we can do is we can, well, might as well define p of x to be equal to x cubed and then minus 2 times a times x squared, making sure we got the multiplication signs in there, and then minus 1. And then we're just simply going to solve p of, and we want to plug in -2, and we expect to give us 5. So this is equal to 5, and we're going to solve for that a value, and we get a equals -2. So the answer is E. Next up, question 3. What do we have here? We have derivative, we have the function we need to find. So this is just integration, so we can just do shift plus for integral, and we're going to integrate 2 over the square root. I'm using SQRT on the keyboard because it's easier to type in, and 2x minus 3, and we got a dx. Let's see what function gives us. We got a 2x minus 3. Now we're also going to make sure, and we should have the constants there. So what we can do is we can perhaps solve this guy plus c. And what do we want to solve this for? So this function value needs to be equal to 4. So equals 4. We're going to solve this for c. But we want to restrict our attention to x equals 6 because that's what we plug in. So c equals -2, so we want that function with the -2, so it looks like it's going to be C. So question 4, looks like we got general solutions going on over here. So the CAS can take care of that for us, so we can just simply solve. Let's see, we got the 2, we got the cosine, we got the 2x, we got the negative pi over 3, and we have a plus 1 equals 0, comma x. Let's see what that gives us. It gives us stuff over here. I remember this question kind of annoyed me a little bit for some reason. So let's see if we can match things up over here. So we got, if you see n1, that's just some kind of integer. So we have 6 integer minus 1. So it's looking like option D here, or actually C would work as well. So we're kind of between C or D. I don't think I can see any others here. And then we got 6k plus 3 or 6k plus 2. So it's either C or D, but I think we have to go for D here, because if you take a look at that second part, if you kind of cancel the 2's out a little bit, this is going to be 2, this is going to be a 1. So 2 integer plus 1, and then this is divided by 2 here. That's exactly what we have in this second part of the output. So therefore, should be D. Question 5. A graph looks like it's a ratio of 2 linear functions. D is the maximal domain, has asymptotes. So if you have the ratio of 2 linear functions, this is actually a hyperbola, and you can get the hyperbola form by just typing in expand, and we got division, got the 3x plus 2, and then 5 minus x, and looks like we got this type of hyperbola. So you can see the horizontal asymptote, this is y equals -3, so looks like it's C or E here, and the x asymptote, it's exactly 5, so it has to be option E. Perfect. Okay, so let's take a look at question 6 now. Looks like we have a derivative, and we want to kind of go backwards from the derivative up to the original function. So how do we usually do this here? So you want to take a look at the zeros of the derivative. So got 1, 2 over here, because those will correspond to turning points on your original function. Also got to determine the nature as well. So this one, it's going from positive up over here to negative values. So if you draw the little sign diagram, it's positive, stationary points negative, so we got a local max, and then the other one you can check it's negative 0 positive, so negative 0 positive, it's a local min. So looking for 2 turning points on the left hand side which go max and then min, and looks like option B does the job here. So because we have the max here, we got the min. D wouldn't be because we've got the turning points on the right hand side, and A, C, and E both have turning points on both sides. We only want turning points on the left hand side, so we're going to go with option B. So question 7, we got a function e to the g of x squared, where g is a differentiable function, and we want to find f prime. So this is just chain rule over here. So let's see, the outside function is e to the something. So how do you differentiate e? Well, it's just the same thing. Let's write this in blue actually. So it's going to be, oops, I want a smaller one. So e to the g of x squared. Okay, and then you have to multiply by the derivative of the inside. What's the derivative of the inside? Well, it's the derivative of g of x squared. But then we have to use chain rule again, I guess. So how do you differentiate g of x squared? Well, first of all, the outside there is g. So because g is differentiable, we can just write g prime of x squared. And then you also got to multiply by the derivative of the inside. So this is like 2 layers of chain rule here. So the inside of the inside is the x squared, the derivative of which is 2x. So we want a 2x g prime of x squared, and I think option C does the job over here. And yeah, it can't be E, so it's C. Question 8. Items are packed in boxes of 25 and the mean number of defective items per box is 1.4. Assuming the probability of an item is defective is binomial, so we have binomial probability here. The probability that a box contains more than 3 defective items, correct to 3 decimal places, that is an absolute mouthful. So we have 25. So we have, looks like we have the number of trials here. So this is kind of like our n. The mean number, so the number, this is the average. So if we say x is binomial, and we want some n and some kinds of p over here, we know n has to be equal to 25, right? And when we're given the mean number of these, or in other words, e of x, if you want, has to be equal to 1.4. How do you get e of x? It's n times p equals 1.4, but n is 25, so 25p equals 1.4. Therefore, p has to be equal to, let's see what that is. So we got 1.4 divided by 25. That is something. So we got, yeah, oops, 0.056 is the p value. Okay, so yeah, we might as well just write it in over there. So 0.056. So this is our binomial distribution, and so we're after the probability that's a box contains more than 3 defective items. The PR x greater because more than 3. So x over here, just to make sure we're clear, x is counting number of defective items. So that's our random variable x there. So how do we do that? Well, it's just menu 5, 5b. So we want CDF because we're going over a range. Number of trials, 25. Probability of success, 0.056. Lower bound, we're actually going to start at 4 because we're not including 3. And upper bound is 25. And that is going to give us 0.048, and that is option B. So that's the answer. Okay, question 9, we got integrals with transformations. These are always kind of fun to figure out. Okay, so how do we go about doing this here? First of all, what is that 2 then? That 2 is a dilation by a factor of, let's see if I remember, it's a half from the y-axis. So half from y-axis. We're just making our notes over here, and that +2, this is a translation left by 2 units. Right, so let's think about how this affects our interval of integration. So originally, it was from 4 to 8. Now what happens to this interval if we dilate by a half from the y-axis? So the y-axis is sitting over here somewhere. If you dilate it by a factor of a half, then this interval becomes 2 to 4. And then we translate left by 2. So if you take a look at this order over here, it's dilations first, and then we do the translation. It's going to become 0 to 2. So in fact, this interval over here, it kind of matches with this one once we apply the transformation. Okay, so we know integral of f of x, it's some wavy function up over here. This area over here, this was originally 5. We did the dilation. So in fact, if you dilate from the y-axis, this area cuts down by a factor of 2. So this becomes 5 and 2 now. And translations don't really, they don't affect area at all. So this should also be 5 over 2. Hence, the answer is E. Hopefully that's correct. So question 10. Given that log 2 n plus 1 equals x, the values of n for which x is a positive integer. Okay, so we have x is a positive integer. Let's see over here. So we have, could we rearrange this? So maybe we can write it as 2 to the x is equal to n plus 1. So we want x to be a positive integer. Okay, well, we can also rearrange this for n. So I guess n is equal to 2 to the x minus 1. But if x is a positive integer, then we would want some, well, n is equal to 2k minus 1, where k is a positive integer. So z plus, not including 0. So let's see if any of the options here match up. So we have n to the k, looks like option B does the job here. So 2 to the k minus 1, and k is a positive integer. Perfect. Okay, question 11. The lengths of plastic pipes, normally distributed, mean, and we got some more information here, and we want to find the standard deviation. Okay, so if we want to find the standard deviation, we need to know the probabilities, a specific x value, which we do have, as well as the mean. Okay, so we know this is going to be a bit annoying. I guess the only way to figure out what this probability is to, well, evaluate this guy over here, which isn't too bad to do in the CAS. It's just menu 552. We want to find the probability. So it's a z distribution, so I don't have to touch this. Z is greater than 1.5, so we have 1.5 here. Upper bound is infinity. And we're going to do 1 minus this number over here. That gives us 0.933 and so on. So this guy is 0.9331, yeah, so on. Okay. Then we have the probability. Oops, let's do blue. So we have the probability that x is less than 259. Well, I guess the first thing we would want to do is standardize this. So maybe we didn't even need to do that. So this is the probability that z is less than. Well, how do you standardize? It's 259 minus the mean, which was 250. So we got a 9 over here divided by sigma. So that's the standardization. Okay. So it looks like we don't even need to calculate this probability. So this is equal to the probability. We're given it's equal to the 1 minus the probability, z greater than 1.5. Now that's exactly our complement. So we could actually rewrite this as the probability that z is less than 1.5. And if we can compare the probabilities over here, or the z scores, we have 9 over sigma equals 1.5. That's very simple to solve on the CAS. So I think you would want 9 divided by 1.5. That's the sigma, which is exactly 6. So we will go for C. Okay, question 12. A clock has a minute hand that's 10 centimeters long. Okay. The clock faces with a radius of 15. At 12 noon, both of the hands point vertically upwards, and the tip of the minute hand is at its maximum. distance above the base of the clock face. So we want both hands to be at the top there. So we want the height h of the tip of the minute hand above the base of the clock. T minutes after 12 noon is given by. Okay, so let's think about this one here. We want a function that describes the distance above the base of the clock. So first of all, we have a mean position of 15 over here, which is why all these are 15, and our amplitude is 10 because this minute hand is going to go up and down by maximum of a distance of 10. Okay. Now we want to start at 15 plus 10, right? So we want to start at a maximum. So we want to figure out which of these functions starts at a maximum. So it can't be sine because sine starts at the mean position. Can't be negative sine so it can't be the sines here. It has to be the cosines then. All right, so both of these look promising because it's a 15 and t is the time after noon. So at t equals 0, we want it to be all the way at the top. So it's either D or E. The only thing that separates these two is exactly the period. So we have to figure out what the period is. Well, that's not too tricky to figure out. It's exactly 60 minutes. Right. So how do we get the period? Well, first of all, you would have learnt the formula period is equal to 2 pi divided by the n value. We want the period to be exactly 60 minutes. So this is equal to 2 pi divided by n. And if you do a bit of rearranging, you find that n is equal to pi over 30. So therefore, it has to be E. So that's question 12. Question 13. Oh yeah, the transformations question. So this one, I think a lot of people got wrong, mainly because of these brackets. You don't usually see transformations where you have the xy paired with the translation matrix, and then you apply the dilation matrix. So you have to think about this one a bit carefully. First of all, if you're used to DRT, then this is a bad form to work in. You want to rewrite this a little bit. So this is cosine. Let's factor out the 2. So we've got a 2 and then a plus x plus 2 there. So this is a dilation by half from the y-axis. And that x plus 2 there, this is a translation to the left by exactly 2 units. Okay, so we want to find the correct transformation matrix. And you might notice that some of these have brackets, which is a little annoying. Okay, so I think a lot of people ended up going for, I think it was C, because we have a half here and then we have the 2 here, so it looks like it matches up. But it's only C if you don't have the brackets over here. And because there's brackets over here, in fact, if you multiply that a half into there, that's only a translation by -1 units to the left. So let's take a look at a few of these. D probably wouldn't be the correct one because we have a 2 here. E wouldn't be as well because we have a 2. So we want a half as the dilation. So it's A, B, or C. We know it can't be C, so now it has to be A or B. So let's take a look at B. We have the dilation of a half here, but then we translate 4 units to the left, which is not quite what we want. We want only a translation 2 units to the left. So we're kind of going for A here. Now the reason why A makes sense is because we have these brackets. So if you multiply in, so you multiply this matrix over here, that makes sense. You multiply a half into that's a -4. That gives you the -2 that we were after. So therefore, it has to be A. So question 14. Random variable, normally distributed, mean twice standard deviation. We're given a probability and we want to find the standard deviation. Okay, so what on earth are we dealing with over here? So we have the mean of x, so mu, has to be exactly twice the standard deviation. We're given a probability and we want to find the standard deviation. Okay, so let's just start by standardizing because we don't even know what's mu and sigma are. So if we standardize this as PR, Z is greater than, well, 5.2 minus mu divided by sigma, but sigma is exactly mu divided by 2. So might as well write it like that. And this is equal to 0.9. And using the inverse normal, we should be able to figure out what this guy is equal to. And from there, we just solve for mu. but I guess we might as well rewrite this in terms of sigma because we're solving for sigma. So let's rewrite it as 5.2 minus 2 sigma because that's mu, and divide this by sigma instead, and that's exactly 0.9. So let's inverse normal this. So we got menu 553, and the area. Now you have to be careful. Don't put in 0.9 here. You got to put in 0.1 because the CAS assumes the area is on the left hand side of the z-score. So it's 0.1. This is greater than. So we have to do the other side. And let's click OK. So negative 1.28 should be this particular value here. So what we can do is we can just solve. We have 5.2. Let's do a fraction first of 5.2 minus 2 sigma divided by sigma. That has to be equal to that particular z-score we found, which was, yeah, the value above. So we take this guy, let's solve for sigma, and we get 7.23. So it has to be option A. Let's take a look at 15. So 15, this is the average value question. Okay, so part of the function f, average value of f over this interval is, so we have, well, we can break this up a little bit. So we got this section on the left and another section on the right. You can take a look at the average values on each side and then take the average weighted value, whatever that means. So on the left hand side, we have 1, 2, 3, 4 squares across. And the difference in height, that's 1, 2, 3, 4, 5, 6. That's divided in half. So 1, 2, 3. So we're only going to go up to here. So on the left hand side, this is the average value. It's how much is each square? Like a on 2. So it has a height of a on 2 here. Now on the right hand side, it should be, well, it should be right over here. Let's use a different color for that. So the average value is sitting right over here on the right hand side, right? Because we're just a straight line and that point is basically halfway through. So we're kind of looking for a value between 0 and a on 2 because that's the average roughly of these two. So we have a on 2. Now it actually can't be a on 2 because on the left hand side there's more volume if you want to than on the right hand side. So there's not an even split. So this is not correct. 0 can't be correct because you have an average value of 0 on the right hand side. It should be pulled up a little bit by the left hand side. Can't be a either. A is too big. So we're kind of stuck between a on 3 and 3a on 4. Now we might as well notice one more thing as well. It can't be 3a on 4 because each of these squares is only a on 2. So 3/4 of an a would actually be sitting all the way up over here. That's too big, that's out of range. So it should be a on 3. So a on 3 would sit right over here, slightly above halfway of a on 2. So it's probably over here, which makes sense because there's more volume on the left hand side. So this average value should sit closer to the average value on the left hand side. So let's take a look at 16. So we got a right angle triangle. It's formed on the horizontal axis. And we have a point over here. We want to find the maximum area of the triangle. So this is just a standard optimization question. So what do we want to optimize? The area of the triangle. So let's try to find an expression for the area of the triangle. So we have the point C over here at m, 9 minus m squared. We're going to, let's define a of m, so the area dependent on m. That's exactly a half. And we're going to multiply this by, well, the base, which is m, times the height, which is 9 minus m squared. That should be right. And then we want to find the maximum area. There's multiple ways you can do this. You can differentiate, but I'm actually going to use one of my programs because why not? So we're going to go analyze, and we're just going to plug in a of m, comma m, and don't need a domain. And looks like the stationary points, the local max is at 3√3. So it has to be option D. So yeah, if you want to do this without the programs, if you don't have it for some reason, then what you can do is you can just solve wherever, if you have the derivative, so derivative with respect to m of a of m, you want to solve this derivative equal to 0 with respect to m, and you get those values, but then these are only the m values. You want the a values. So what you do is you have your function a of m such that, well, you only really want this condition over here, and you get 3 root 3. So question 17, we have a function, we have the tangent, has a vertical axis intercept, so y-intercept at 0, c. The maximum value of c is... Okay, this one's interesting. How can we do this over here? So we kind of want the tangents line equation, so we can do that by going to calculus, and we got the tangents line, and let's plug in negative ln for natural log of x plus 2, and then we're going to go comma x, and we want to be at some points. Let's just choose a random point. Let's say a. Well, let's not do a actually, because a is already defined. Let's do b. So this is the tangent line equation. Now this part over here, that's the y-intercept which we want. And what we want to do is we want to maximize this y-intercept. So again, you can define maybe y, I don't know, y-ints of b. So the y-intercept dependent on b to be exactly this part. And let's include the negative sign as well. And then we just need to maximize once again. So we're going to solve where the derivative of this thing with respect to b of y-int of b is equal to 0, comma b. We got b equals 0. So let's see what happens at y-int at 0, and we get negative natural log of 2. So that looks like it's option C over there. Right, and once again, you can use the programs if you have my program, so you can just plug it into the analyze program. Let's actually try to do that. So let's go to the book button, functions, analyze, and we're going to have a look at, we want to maximize the y-intercept, right? So y-int of b, comma b, don't care about domain, and yes, indeed, this is the local maximum, natural log of 2, so we'll go with C. Okay, question 18, we got a function. Looks like it's a hyperbola. The range of h is... Okay, so let's think about what this hyperbola might look like. So, well, here's the axes. Here's the horizontal asymptote. So this is y equals b. So it's probably going to be sitting like this somehow. So A is A positive. Yes, A is positive. So we can assume we have this shape over here where it goes top right and bottom left. Now we want to go from negative a, so including this point, so negative a to 0, and we exclude 0 for obvious reasons because of the asymptote, and we go up to a, so something like this. And we want to find the range, so we would ideally want to include this point. We also need to include this other point up over here. And the range looks like it's going to be everything down here, everything up over here, and we don't include anything in the middle. So what happens when we have x equals a? Well, first of all, this is the left-hand side should be negative a. So if you plug in negative a, you're going to get a negative 1 plus b, so that's a b minus 1 over here. And the y value on this right point, that's going to be, well, if you plug a in, you're going to get 1 plus b, so b plus 1. So for you guys, you can see where those y values come from. And we want to include the points at b minus 1 and b plus 1. So it can't be b over here, and it can't be c. So it kind of has to be a, d, or e. Now it can't be a because a is an interval between these two y values, which we don't want, so it can't be a. And it can't be E either because E just says go from B minus 1 and just keep going upwards, which is definitely what we don't want, so it has to be D. So D is what we want because we go from negative infinity up to that point B, and from positive infinity down to the B plus 1 there. So yeah, should be D, hopefully. Okay, question 19. So question 19 and 20. I remember these. These were the worst two questions, but I managed to find a way to kind of simplify the explanation. So let's see over here, we have P probability function for the number of times that a 6 is rolled. Okay, so this is a binomial distribution. Because we're doing a number of trials, they're all independent. Now Q is the number of times that a 6 is not rolled. So we have kind of like something that determines, so we have something with successes and something with failures, and we might as well define things that way. So we might as well define a success to be a 6 is rolled. Right, so first of all, let's think about what the function P is doing. So what on earth is P of X? P of X is the probability that we get 6 or X 6's rolled in 20 trials. Or in other words, it's the probability that we get X successes. And what is Q of X or Q of W? Q of W is the probability that we get W non-6's, or in other words, we can say W failures. Right. Now, notice we want to rewrite Q in terms of P. Right, so Q is a function with failures. We want to represent that somehow in terms of successes. And a nice thing about binomial probability, in particular each of the trials, is that it can only be either successes or failures. So if you take a look at all the successes, so X, and you add it with the W, it has to give you the number of trials. So X, this is number of successes. Oops. And W, this is number of failures. Altogether, there should be number of trials, because it can only be success or failure. So therefore, Q of W, well, this is W failures. We kind of want this to be in terms of successes, but notice that's really the same thing as the probability of getting 20 minus W successes. Right, because if 20 minus W of them are successes, then the remaining W must be failures. So this is equivalent over here. So we reframe this in terms of successes. Now, this is nice because we have a function, P of X. So we have P of X is X successes. Now, if we have 20 minus W successes, well, that's the same thing as P of 20 minus W. So we've written Q in terms of P, which is quite nice. So therefore, answer is A. So now for the final, probably the most trickiest question of this whole exam. So f is a cos function. We have the a constant in there as well. It's a function with this property. So f of x is equal to f of x plus h. And notice h is an integer. So in particular, for all values of x, if you jump forward by an integer, you should get back to the same y value. Or in other words, this function is periodic, so it has an integer period. Now, notice one key thing here. This says that it has to be true for all h in z. So z could be 0. So if h is 0, this is obvious because f of x is equal to f of x. But it also has to be true for h equals 1. So f of x equals f of x plus 1. So the period is actually 1. But how about if h is equal to 2? Well, if the period is 1, then it's obviously going to be true for h equals 2 as well, and h equals 3. So if you imagine a little cos graph over here, if your period has to be equal to 1, right? So this distance here, this has to be equal to exactly 1. The period is also 2, so it makes sense for 2 as well, and 3. And because we want this for all integers h, our period has to be precisely 1. Right, so we know f has a period of 1, so f period equals 1, so we can actually figure out what the a value would be. Right, so the formula for period, it's t equals 2 pi divided by n. We want t to be equal to 1, and this is 2 pi divided by n, so therefore n has to be equal to 2 pi. So therefore we can rewrite our function f of x to be equal to cosine of 2 pi times x, which is quite nice. Right. So next up we have a new function g. This is log base 2 of f of x. So let's think about what the log base 2 function looks like here. So I'll do this in yellow. So here's the xy axis, here's the log base 2 graph, and you have your x-intercept at 1 over here. Okay, now we want a function with the range of -1 to 0. So we're only interested in the values down over here. So -1 to 0. We're only interested in these values. So what are the possible x values we need to put into the log base 2 function? It has to be from 1/2 up to 1. So if you're on this interval here, then you're guaranteed to have a range of -1 to 1. So in particular, we want the domain of log base 2 to be 1/2 to 1. Because that guarantees a range of -1 to 0. Now notice this is not just log base 2, it's a composite function because we put an f of x in there. So if the domain of log base 2 is 1/2 to 1, that means that the range of f of x has to be 1/2 to 1. So this tells us the range of f of x is precisely, well, 1/2 to 1. If we can get the range of f of x to be on this interval, then that guarantees that the range of the overall function of the log base 2 function is between -1 to 0. Okay, so we know what our function looks like. It's cosine of 2 pi x, and we also know what range we need to hit. The final thing we need to figure out is the domain for d. So how do we get that? Well, let's draw up a little function over here, and I think I might do a few periods on both sides. So we have, oops, we got one period, and let's do another one as well, and let's do maybe one on the left hand side. I think that should be enough for all the answers that we could have. So yeah, we know the period is 1, so let's label. So we have 0, and we have 1 over here, and then we also have 2, and we got -1 over here. Right, now the nice thing, if your mean position is exactly 0, then every quarter of a period you actually alternate between turning point and x-intercept. Right, so in particular, for example, this point over here, this would be a quarter, and we also got 3 quarters over here, and you can fill in the gaps. This is like 5 quarters and, I don't know, 7 quarters, I think, probably. And yeah, on the left hand side, it's -1/4, and we also got -3/4. So I think that should be sufficient. Now, what did we want? We want the range of f to be on the interval 1/2 to 1. So we want the values above 1/2. So let's draw a line up over here. That's the values we want. So in particular, our domain can only lie in the regions where our function is above the line y is equal to 1/2. And yeah, because the maximum value of cosine is 1, yeah, as long as it's above, we can ensure that it's within the interval 1/2 to 1. Right, so hopefully that is clear there. So maybe I'll draw in another line. So this is the line y equals 1 if you want. So we want a domain which only covers these areas here. Okay, so we start searching for possible domains. The only way you can do this is trial and error, really. So let's take a look at A, and we got 1/4 to 5/12. So, I mean, already A wouldn't be an option because you're starting at 1/4, which is outside of that yellow band there. So A wouldn't be right. Let's take a look at B. Now B looks promising because we start at 1, so we're starting within that yellow band, and we're going to 7 on 6. Now 7 on 6, you can check on your calculator what that is. 7 on 6, that's roughly 1.1. That's actually less than 5/4, which is 1.25. So you're actually starting at 1, and you're only going, well, a little bit further somewhere. So B looks promising. Let's just mark that in case it is the correct one. C, it's 5/3 to 1/2. So 5/3 is like 1.4, I think. Now 1.4, that's beyond the 5.4 over here. So we're starting over here and we're doing something else. So it's already outside of the yellow band. Option D, we're starting at -1/3 to 0. I believe this was actually the one I answered on the actual exam. Turns out that's wrong, because 1/3, that's a bit further out than -1/4. Right, so -1/3 would probably be here, and as you can see, it's already outside of that yellow band. Right, so if we start down here, that's -1/3, it's outside that yellow band, so it can't be D. And E, -1/12 to 1/4, which kind of looks promising because -1/12 is right in here, right? But then the unfortunate thing is he ends at 1/4, which is down here, and that's outside of the yellow bands. So you always want to be inside of the yellow bands because you want your range to be a half to 1. So therefore the only option should be B, because B starts, well, inside the yellow bands. So it starts at 1 and ends at 7 on 6. And you can actually check what happens at 7 on 6. So we had 2 pi times x, but x is 7 on 6. It actually turns out it's exactly a half, right? So in fact 7 on 6 would land you right on the other side of the yellow band. So this would be the domain that we want. So this was a really challenging question. I don't know how long it took me to even explain this, but oops, not even D. But yeah, it has to be B. So I think I chose D. I believe the reason why I chose D was because I could make the value work. But it turns out if you choose D, then you have to have a period of a half, I think, or maybe 2. I'm not too sure. I forgot, so you can probably check it. But that actually means that the condition that we have the period of 1 fails, the period actually becomes a half instead. Right, so the only option would be B. Okay, so that's multiple choice. So yeah, this was a pretty tough set of multiple choice questions. So yeah, hopefully you guys found this useful. I'll probably do the second part, so part B, or extended response or short answer, whatever it's called, in another video. But yeah, that's all for today. Thank you guys for watching. Hope you have a wonderful day, and I'll see everyone again next time. Bye bye.